Hello everyone, this is Team Sleep Learning and we are here to present to you our project Stereo Disparity Estimation from Low Texture Thermal Images. First, let's understand what exactly is stereo disparity. It is the difference in the position of an object as seen from the left and right camera due to physical separation between cameras. It infers how far an object is from the cameras, which in this case is point PL as seen in the diagram. This can be related to a biological phenomenon, which is how your brain perceives depth from left and right retinal images. Now let's take a look at our problem statement. There is a need to estimate stereo disparity in autonomous driving applications to know the exact location of an object. Since LiDARs are very expensive nowadays, the industry is gradually trying to adopt vision-based methods to solve this problem. Traditionally, RGB images have been used. However, quality of RGB images suffers in low light, in extreme weather conditions, and from incoming glare from the car headlights. With erroneous results, it can lead to more accidents in an autonomous driving setting. One solution to this is to use IR images. These images are robust to ambient illumination, fog, and glare due to incoming car headlights. Secondly, they embed the thermal components emitted by the objects, which makes them favorable for a low light setting. And even though they are low textured and extremely noisy, we have explored a pre-processing technique that alleviates these issues to an extent. But despite of this, there are a lot of caveats which we came across with respect to the IR images. First is that they are very low textured as compared to the RGB images. As a result, feature extraction becomes an issue while using convolution layers of a neural network. Second, they are extremely noisy. As you can see here, if the noise equivalent temperature difference of the thermal cameras changes even slightly, there is a huge impact on the quality of measurement. Third, for our datasets, IR images have a low resolution as compared to KT15 RGB images, which have been used as the standard data for most stereo disparity estimation tasks. And finally, because of having so many caveats, it is quite an unexplored field, and hence there is hardly any prior literature or model architectures to refer to. Yet we have tried our best at this very interesting and unexplored problem.
These are some of the tasks we aimed at performing. First was to find a proper pre-processing step to retain the features in low-texture IR data. Second was to build a model efficient enough to capture details in these images to generate disparity maps. Third was to find an evaluation metric to estimate the disparity error. And finally, our goal was to evaluate this step with two datasets, CATS dataset and the CMU dataset. The CATS dataset consists of 179 IR images, which are the left and the right stereo pairs with ground truth disparity captured using a LiDAR. The resolution of the images is 480 by 640. We made an assumption that this dataset will work well with existing disparity estimation networks that only work with RGB images. Next is the CMU dataset. This is an unpublished dataset which we were given access to by Scilab at CMU. This dataset consists of 200 IR images with ground truths captured using LiDAR. Examples from left-right stereo images and ground truths provided by this dataset are shown. For the data pre-processing part, we tried a lot of techniques, and the ones that worked better than all the others were the Inferno color map and CLAHE, which stands for Contrast Limited Adaptive Histogram Equalization. Next, for experimentation, we mainly tried out three state-of-the-art models as our baseline architectures, the ANet, the Garnet, and PSMNet. However, as these models are defined and constructed for RGB data, they did not extend well with our IR dataset. Hence, we modified the existing PSMNet, added CLAHE preprocessing, and used the super-resolution network for post-processing, which fit well with our problem statement. Let's take a look at this specific model in brief.
This is the architecture for our best performing model. We process the left and right images with CLAHE and pass them through a CNN feature extractor and a pyramidal pooling block. The weights of these modules are shared for both left and right images. We aggregate these features to construct a 4D stacked cost volume and compute a disparity estimate. Soft augment regression was used to construct a continuous disparity map with smooth element loss as a divergence. We then pass this computed disparity map through a 5-stage SR network to compensate for the loss resolution, which is trained using MSE loss. Here we can visualize the results obtained using our super resolution module. The ground truth disparity is downsampled by a factor of 20, which makes it extremely pixelated. We then use the SR module to recover the image back. We obtained an impressive PSNR of 53 decibels. This is a higher level view of our project. The left and the right stereo images are passed as input to our stealth pipeline. We then pre-process these images, pass them through the disparity estimation network, followed by the SR network to get an output disparity map.
Now that we have the predicted image, we can compute the disparity error. It is the percentage of outlier pixels in the image. There are two constraints in this. The absolute difference between the ground truth pixel value and predicted pixel value has to be lower than T1, and normalized value of that difference should be lower than T2. The points satisfying these constraints are classified as inliers, and the percentage of outliers become our disparity error. In the error visualization, the first image is the predicted image, the second one is the ground truth, and the last one is the disparity error map. The regions with cooler colors indicate correctly predicted points, while the warmer colors show the outliers. Here are the results of the D1 error computed for all the model architectures we have tried out and the different pre-processing and post-processing steps. Among all those we have tried, we see that the images when pre-processed with CLAHE and acted upon by our network gave the lowest D1 error of 34.9%. So we conclude that the SOTA models for RGB images do not work well with IR images. But when these images were processed with CLAHE and SR, the network extracts and learns meaningful features. In the future, we plan to speed up the performance of the existing model and to improve its architecture to generalize better so that it can be incorporated in autonomous driving systems. Thank you, and please reach out to us on Piazza.